Welcome back, everyone. Let's go over the solutions for the k-nearest neighbors exercise project. All right, here we are back at the exercise notebook. What we're going to do is begin by starting with the first task, which was to run the cells in order to read in the data. So we saw here, it's a pretty simple data set. We have those 60 frequency columns and then one label column. For data exploration in this case, we just asked you to create a heat map of the correlation between the difference of the frequency responses. So for this, we're going to say plt figure, and we'll set that up with a fig size equal to something like 8 by 6 to match a larger figure size here. And then we can create a heat map. In this case, all we need to do is pass in the 𝑷𝒓.𝒐𝒂𝒔𝒊𝒐𝒏, which is correlation call. And if you run that, it will default to this kind of magma distribution for the color mapping. But we'll go ahead and change the color mapping to be cool warm to match what we have in the solutions. All right, so something you should notice here is obviously you'll have a direct 100% correlation diagonal line because every frequency is going to be directly correlated with itself. But what you should also notice are these kind of reddish zones between frequencies that are close to each other. And that's a good indication that these are probably informative frequencies, that they have a signal to each other. It makes sense that a frequency like 13 or 15, since it's ordered by the actual frequency or wavelength of that signal that's being sent out, that frequencies near each other should probably also be correlated to each other. And that's why you get this kind of pinkish zone or kind of light red zone in certain spots where frequencies tend to be correlated with each other. All right, so we'll go ahead and move on. Not too much to visualize there of 60 frequencies. And next task is, what are the type 5 correlated frequencies with the target label? So because of the target label being in letters R and M, what we have to do is you have to actually first map this to a 0 and 1. So what I can go ahead and do is the following. I can say df create a target column and have that be equal to the label column, where I simply map rock, and this has to be a dictionary. So I map rock to the number 0, and I map mine to the number 1. So if I run that mapping sequence, then I should now be able to see with my data frame that I have 62 columns. If I go all the way to the right, I now see this numeric target. And the reason I need to do that is because I can't really find the correlation between a letter, but I can find the correlation between a 0 and a 1. So now what I should be able to do is actually rerun this right here, and you should notice a kind of last new value called target, and I can see how correlated everything is with the target, and that's that last column. So if I actually want to see that numerically instead of visually, what I can do is come back here and say find df correlation, and then only grab this target column, and I can see how correlated everything is. And in regards, we're looking for the things that are most correlated in the sense that we're looking in terms of absolute correlation values. So in this case, if I just say sort values, I may have certain negative correlations that are higher in terms of absolute value than the positive correlations. In this particular case, it doesn't look to be true. It looks like these top 5 correlations are actually have a higher absolute value than these. But if I wanted to make sure that, I could just say np.absolute value of the correlation first, along with the target, before I actually sort the values. So you run that, and then we should be able to then take the tail end of this and take, for instance, the 5 right here, which is frequency 11, 12, 49, and 10. And we actually asked for the top 5. So because one of these includes target itself being perfectly correlated, we should actually make this tail 6. And there we go. We have top 5 highest correlated frequencies in terms of absolute value. After this, we'll go ahead and move on to the train test split. This should be pretty straightforward given everything we've done before. We're going to say from scikit-learn.model selection import train test split, and then we'll set up our feature. Recall that we did create another column called target. So for the features, I'm going to drop both that target column that we created and then the original label column. And we'll set this along x is equal to 1. Then for my y value, that's simply just going to be that original label column, an r or an m for a rock or a mine. And then after this, it's go ahead and do the train test split. So we'll say train test split, shift tab, expand on this, and what I'm going to do here is just scroll down like we always do and copy and paste this right here. And to match up with the solutions, what I'm going to choose is a smaller test size. Since we will be performing a cross-validation or grid search, technically this is acting more like a holdout test set. So because it's kind of a holdout test set, I'll make this test size smaller, just 10%. And I will go ahead and keep 42 as the random state. So run that, and now you have your train test split. And now it's time to create a pipeline that contains both that scalar and the KNN model. To do this, first thing you have to do is actually import what we need. So we'll say from sklearn.preprocessing, import the standard scalar, and we'll also say from sklearn.neighbors, import the kneighbors classifier. Then we create an instance of the bare case for a standard scalar, kind of the default standard scalar, just as we did in the lectures. And then we'll also create a default kneighbors classifier. Then we have to decide the order of operations we want to perform using these tuple pairings. So just before, we do the scalar first. So pass in scalar, and this should be a list. So let's put in the brackets there. And then the next option is KNN with the KNN variable. And there's our order of operations that we're going to pass into the pipeline. So let's go ahead and create the pipeline object. So we need to actually import that as well. We'll say from sklearn.pipeline, import pipeline. And we simply say pipe is equal to this pipeline, where we pass in these operations. So we have our pipeline ready to go. It will scale the data according to this default standard scalar, and it will also perform a k-nearest neighbors classifier using defaults. However, we do want to perform a grid search to figure out the best values of k. So I need to pass in a parameter grid dictionary that knows it's going to look at this KNN inside this set of operations. To do this, we'll construct the following. We'll say from sklearn.modelSelection, import grid search CV, and then we'll say from k-values, go ahead and make a list, and I'll check k-values all the way from 1 to 30. It's the computer doing the work, so it's not a big deal to make this a relatively large range. And then we set up our parameter grid to match up those values. And recall what we have to do here. We have to say the string name of the operation, in this case KNN, so it has to match right here, KNN, KNN, then two sets of underscores, underscore, underscore, and then the actual parameter, which is n neighbors. So as we discussed in the lecture, it has to follow this exact key method. And then here we'll just pass in the k values. So we have our parameter grid. Next, what we're going to do is actually set up the classifier. So we'll say full cross-validation classifier is equal to an instance of grid search, pass in the pipe, pass in the parameter grid, and then we can choose some CV fold like 5-fold, and scoring will base this off accuracy. So we can run that, and then we can go ahead and fit this full CV classifier to our X train and our Y train. So you run that, and now we went ahead and fit this. What we can also do is after we fit this, we can grab the best estimator. So I can say something like full CV classifier dot best estimator, and then I can get the parameters here. So I can say get params of the best estimator. The reason I have to say best estimator off of this instead of directly get params as we did before is recall that this classifier technically has a scalar inside of it as well. So what I'm saying is find the best estimator, and I have this kneighbors estimator inside. So we'll go ahead and check that, and I can see that it looks like it decided that the best number of neighbors was actually just one neighbor, which is kind of interesting. And what we can do is we can actually create a plot, which was this hard task, which is to see if you can plot the mean test scores per k value. So what does this actually mean? Well, it ran a bunch of different combinations of all those cross-validations of various k values. At the end of the day, it found that just using the first neighbor actually has the best accuracy results. So if I take a look at this CV results dictionary, so that would be full CV classifier, CV.CV results underscore. If you take a look at that, it's this kind of huge dictionary, and I could actually pass this into a data frame. I can say PD data frame, and organize it that way so I can see the results here. And you'll notice it has the information, and we've seen this before. It has the mean fit time, standard deviation of fit time, score time, standard deviation of score time, the parameter being used, so 1 neighbor, 2 neighbors, 3 neighbors. And then we can go ahead and scroll over to the right to see some other columns. Scroll over, and you'll see the various split test scores as well as the mean test score. So that means off of this, what I could grab is the mean test score column. You could also do this as grabbing this a key. And here are all the mean test scores. Notice that it's in order for K1, K2, K3, and so on. And in fact, I can actually just call plot on this to plot this out. And this is using Pandas plotting. So I can see as K increases, the accuracy actually goes down. So this is not the typical elbow graph that we've seen earlier, because I'm actually plotting accuracy, not loss. I'd have to say 1 minus accuracy, and that would essentially be the invert. You'll realize that as K increases, you start to go up. So in this case, kind of a special case of the frequencies where you should just look at the nearest neighbor, just one single nearest neighbor, to get the best results. Anything higher than that, and you're going to start losing accuracy. So again, what we've seen here is based off the mean test scores, you should just use one neighbor. And as you actually increase K, you start to decrease the accuracy. Okay, so now that we understand that, what we can do, you can check out this plot right here, similar plot, is a final model evaluation. So to do this, we'll simply say my predictions. So 𝑦pred is equal to this full CV classifier, predict oft x test. I don't need to scale it because it's actually going to be scaled internally. And let's create this confusion matrix by saying from sklearn.metrics, import classification report. And then we can also import the confusion matrix. Run that, and then we'll say confusion matrix of y test versus y predicted values. And you should get the same results if you use the same random split and set up your model the same way, where we actually only misclassified 2 points. But however, the thing to notice is one of these is a false negative, essentially telling you that it's actually a rock when in reality it's a mine. So that's a major problem if you're a submarine. So we may need to, again, kind of revisit this with some maybe ROC curves and see if there's any way we can trade off false positives versus false negatives in order to improve performance and make sure that we always classify something, if we're not sure, as a mine versus accidentally classifying it as a rock when it's actually an explosive mine. And then we can also print out the classification report. We can see y test versus the predictions, 𝑦pred. And again, we get the matching results. Okay, and that's it for the solution walkthrough. Again, let me go ahead and review some important things to note here. As you're creating the grid search, if you happen to be using a pipeline, you have to pay really close attention to the way you discuss this parameter grid. It's this string code, 2 double underscores, and then the parameter itself. Then you can set up your classifier, and there's lots of information you get off this classifier. If you're interested in estimator information, you use .bestestimator underscore, and then you can grab parameters off of that. And we saw here that we can also see the cross-validation results, something we've seen before, as a data frame. And if you want, you can begin to plot off of that. Or what you could do is just grab this as if it was a normal dictionary. So again, you notice here, this itself is a dictionary, which means I could just grab the key value of the dictionary, mean test score, to get the same array here. And from there, you can start plotting it. So you can say plt plot, and then you would say plot k values versus the mean test score. And that would show you the exact same plot. All right, that's it for the solution. If you have any questions, feel free to post to Q&A forums. I'll see you at the next lecture.